So we have seen that dipoles are created in a dielectric material. Now, when you apply an external electric field on any material, would you have the same number of dipoles be created? Would you have the same amount of polarization? You would not. It depends. The amount of polarization that you would get depends upon the polarizability of the material. Let us look at what is polarizability. So when a material is exposed to an electric field, you will have the creation of dipoles. And if you look at these dipoles aligning themselves in the direction of the field, you see in this internal dipoles, every positive charge center is next to the negative charge center of the neighboring dipole, and so on and so forth. So each of these positive charge centers will be neutralized by the effect of the negative charge center, except you will have a surplus of negative charges near the positive electrode and a surplus of positive bound charges near the negative electrode. These charges are called induced charges. So now you have a polarization, a dipole moment. You have a negative charge center and a positive charge center. Let's say the charge involved is Q. And this Q charge is separated by a distance d. So you have an effective dipole moment that is created. And this effective dipole moment that is created would depend upon the polarizability of the material. This polarizability of the material, the polarization that you have is equal to alpha into E, where E is the electric field. So higher the electric field, more polarization occurs. But it also depends on alpha, which is the polarizability of the material. And polarizability depends from material to material. We will discuss that later. So what you have is, when you have an external field, polarization happens depending upon the polarizability of the material. Now we can define a vector P, which is analogous to the flux density D. If you have free charges within a volume and there is a surface that is enclosing that volume, then the total flux density, the surface integral of the flux density crossing that surface, is equal to the total free charge that is enclosed. Similarly, you can think about a polarization flux density, a polarization vector, and the surface integral of the polarization vector crossing that surface would be equal to the total bound charge that is enclosed by this surface. Remember, the polarization happens in a direction which is opposite to that of the external field. So therefore, QB is equal to minus surface integral of P dot ds. So therefore, we have to now distinguish between free and bound charges. We know that the total charge enclosed by a volume QT is equal to the surface integral of d dot ds, where d is epsilon naught E. So imagine we are talking about vacuum here. So D and E are related by the permittivity of free space. Now let us imagine that instead of vacuum, you now have a dielectric material. If you have a dielectric material, in addition to the free charges, you will now also have some bound charges within the dielectric material. And depending upon the number of bound charges that you have, due to the polarization process, there will be a flux. There will be a polarization flux P, a polarization vector P, and if you were to take the surface integral of that polarization vector, you would get integration P dot ds to be equal to QB. So therefore, you can now imagine that in the presence of a dielectric material, QT is equal to not only the free charge Q, but Q plus QB, where B is the number of free charges. So therefore, Q, the free charge, is equal to QT minus B QB. QT is equal to epsilon naught E within the surface integral of epsilon naught E, and minus QB is plus P dot ds. So therefore, now Q will be related to the surface integral of this entire quantity epsilon naught E plus P dot ds. So instead of having d dot ds, you have epsilon naught E plus P, which means in this scenario, your flux density D must be equal to epsilon naught E plus P. So now you have epsilon naught E, one component of D, plus an additional component of D, which comes from the polarization vector. Divergence of P is equal to minus rho B by definition. And divergence of epsilon naught E, the free space, is equal to the total charge density, which means divergence of D, again, we know by Gauss's law, is equal to rho V, which is the free charge density. So where does this take us? I'll come to that later. But what I see is that in an isotropic material, P and E are linearly related and they are parallel. We will stick in this course, we will stick to isotropic materials. So P and E are linearly related and parallel. We are not going to talk about ferroelectric materials where you have hysteresis. If that is the case, now I have already said that polarization is directly proportional to electric field E. So I can write P to be equal to xi E epsilon naught E, where xi E is a dimensionless quantity which is called the electric susceptibility, and epsilon naught is the permittivity of free space. So therefore now I can write, I obtained in the previous slide, D is equal to epsilon naught E plus P. And P is proportional to E, so now P can be written as xi E epsilon naught E. So therefore D can now be written as xi E plus 1 into epsilon naught E. We also know that D is equal to epsilon E, where E epsilon is the permittivity of the material. So therefore, and this epsilon is what we have called epsilon R, the dielectric constant of the material. So therefore, the dielectric constant of the material can be written as xi E plus 1, which is xi E is the susceptibility plus 1. So epsilon is equal to epsilon naught epsilon R, and epsilon R is equal to xi E plus 1. So therefore, what we see here is that the permittivity of a material, or the dielectric constant of a material, is directly linked to the polarization processes. It is linked to the polarization vector. There are two ways of measuring the polarization of a dielectric material. If you're operating at a molecular level, you can find the polarization as a function of space. But as engineers, we do not do that. We measure polarization as a macroscopic effect, and the effect that we measure is the dielectric constant. So the moment we talk about the dielectric constant of a material, we have taken polarization into account. So a material which has a higher dielectric constant has more polarization, is susceptible to more polarization, has a higher susceptibility, and the use of relative permittivity is to take into consideration polarization, bound charges, dipole moments. The effect of all these things is encapsulated in the concept of polarization and in the concept of, and is measured as permittivity. So polarization is accounted for in the permittivity of the medium. So higher the permittivity of a material, more polarization will occur. It will be able to store more energy, half epsilon E square, and it will be able to, it will be better for certain applications. So when we talk about dielectrics, we're essentially talking about a material which does not allow current to flow through. So suppose you have two oppositely charged conductors, M1 and M2, and they are separated by a uniform dielectric. Then we can talk about the capacitance of this dielectric. The ratio of the magnitude of charge on either conductor to the magnitude of the potential difference between them is the capacitance. C is equal to Q by V naught.